Hello guys, this is the first video for Computer Science 1610, the programming class, and I thought we would start these video lectures by actually going back a little bit to what we discussed in the last class. And some of you guys got it and maybe some of you didn't, so I thought maybe by doing it again it would help everyone get off on a good start with these video lectures. I think most of you are in my physics class as well, so you'll know these are all new to me. So I'm going to try to improve, and if you think of something that I can do that isn't too crazy to make this better for everyone, let me know, and I'm more than willing to give it a try. I suppose anything other than, canceling the final, or I guess we don't have a final, canceling all the projects and homework and just giving everyone an A. So basically anything up to that, I'm willing to try. Okay, so this is the same notebook that we had in class the other day. You might have noticed in the physics class, I had a video of myself because I felt like it would be simplest to work on the board. Here I thought that instead I could show the Mathematica notebook on my laptop as we work through things. And you might notice there's an arrow here. There's some ability here in, I'm using Zoom, but there's some ability here to highlight different places on the screen. So as I'm talking about different points, the arrow will go there. I suppose if we were doing this live, it probably would allow other people to annotate or mark spots, but since I'm the only one here talking to myself, you just see my arrow. Okay, so this is the same notebook we worked through last time, where the goal was to come up with a polynomial which interpolates between data points. So it's important to understand how the data is being stored. And in the examples I do in this class, I will usually write things in terms of a list of lists. So here's an example of what I mean. I have an outer list. This is the outermost brace, and then which only gets closed here at the very end. And then there is inside that a list of ordered pairs, x1, y1, x2, y2, x3, y3, etc., all the way up to n being the last data point. So that's kind of typical of how you might encode data. And of course, the way that you use the data in a program would depend upon the way the data was actually structured. So it's important to understand how the data is stored. So here's an example of a list of points for something. And you can take that list, that table, and we can make it into an actual Mathematica list over here. So if I go over to the place where I have do it indicated, I can make a list called data, which equals, I seem to have had not the right kind of cell. So we'll just get rid of that. We'll try again. Oh, you know what? We'll even cheat. Well, actually, what I'll do is I'll get rid of that, and I will actually type it out just so you can see it. Data. I'm going to make a list of lists. So the outermost list starts here, space so it's a little easier to read. And now I'm going to have a smaller list, x1, y1. So that would be 1, 0. Close off that one. The next entry in my outer list would be 2, 1. Then I would have 3, 3. So now I have, you'll notice here, I have small lists that sit inside a larger list, and I need to close off that larger list like that. Okay, so putting in some spaces there, it doesn't affect what Mathematica does, and it does make it a little easier to view. All right, now go ahead. suppress the output to that. And then I can list plot, and you'll notice that I get data points. It's a little tricky to see. It kind of cuts off the data point up here and the one over here. And if I really cared about this, I would rescale things. You know, I could make the plot range maybe X should go to 3.1 instead of 3, and maybe the lower limit should be maybe negative 0.1 in the Y direction. And then you notice immediately my data points are a little bit more visible, maybe up to 3.3, or 3.1, sorry. And then, oh, wrong spot. Change this to 3.1. Yeah, if I keep tweaking it here, eventually I can get all the data points to show. Okay, so that's how we enter lists. We've seen that before. And you know, in class we talked about how to load it into files and stuff. I'm not going to do much of that right now. What I want to remind you though is how we can pull out little bits of data from a list. So we've defined this list of data points called data, and I can extract the various parts of it. So for example, if I wanted to pull out information, so first off, when you want to extract data, use the double bracket notation. And basically, you're going to give a list of places inside the list, and it works according to the slot of the outermost list to the innermost list. So if I do 1, 2, you would interpret that as position 1 in the outermost list, comma, position 2 in the entry that you pulled, that the 1 referred to. So in this case, I would look up here at the 1, and that would be the first, sorry, this pair right here is in the first spot. The first 1 refers to the first pairing, and then this would refer to the second entry in that pairing. So the answer should be a 0. So let's see how we do. Ta-da! It's like magic. Okay, so that's an important skill to have. As we finish out the semester and we start using programming to compute numbers and to work through the last few projects, it will be important to know how to reach in and pull information out of lists to finish out things, or to manipulate experimental data. All right. Interesting, the little arrow there doesn't move. Okay. I'm getting used to all these little commands, so I apologize. All right, so we talked about interpolation in class, but I thought we'd run through the same information. So to interpolate means to come up with a polynomial, or actually any curve, but it's a curve chosen to hit specific points. For example, if we want to do linear interpolation, that means we want to find a line which passes through at least 2 data points. You need to have at least 2 data points to have a line. That's uniquely defined. All right. So here's an example. In class, I was going to actually have it be kind of an exercise, but let's go through what I've got here. I wrote a little module that will take data, and then also utilize a user-specified variable. It could be anything. Remember, the underscore means that it's an arbitrary, or a kind of Mathematica understands that this is really just a dummy variable, sort of a placeholder for whatever you want it to mean. And then what it does is it converts data into a module, or into a local variable called points. I just did that so that Actually, you know what? You can see what I did here. I even made a mistake because data should be the external global variable or global information. Points is the local information. And then when I wrote my little program here, I didn't even use it. So I better fix that right now. So let's go back. What's the formula for a line? Well, I'm going to use the point slope formula. So that means I want to add the y value of a point. So that I'm going to choose the first point. So I use 0.1 and 2, comma 2 to select the y value, but I should change data to be points. And then I multiply by this, or then I add to that the slope times x minus the x value of that corresponding data point. So I have data point 1, and I pull out the x value. And then I have to reach out and get, oh, I should change that to points. And then I should also compute the slope using data points. So I have y1 minus y2 divided by x1 minus x2. I just need to change that to be points so that and it won't change the way that program really works, but the whole point of using a module was that we were not manipulating the real data, the global information. Instead, the goal was to only manipulate the local information to eliminate the possibility of editing data when we didn't want to. Okay, so that's my module. Very nice. And then here I've defined data as a two-dimensional array, and I applied my function called line of data of x, and I went ahead and evaluated that. And sure enough, I get a line, and I guess I didn't go ahead and show the data points, but it does pass through the data points. Because that's kind of a handy little thing to have at your disposal. Very good. Okay, in class we described Lagrange polynomials, which were a little bit more complicated than just a simple line. So I have a nice, that's my opinion. I have a little blurb here on the big picture idea and then kind of the basic strategy. So the big picture is that when we have n plus 1 data points, in general, you will fit that or be able to fit that to a degree n polynomial. Notice, n plus 1 points goes to a degree n polynomial. For example, here, I'll type it here. 2 points fit a line which is a degree 1 polynomial because the highest power of x is 1. All right. Lagrange found a nice formula for such an interpolating polynomial. It's nice because it's pretty handy and a human can just pretty much crank through it as fast as you want. It's not it's not always the best or most efficient way to do it, it turns out. As we will see, every time you add a new point, you have to go through the whole process again and reconstruct the Lagrange polynomial. There are other ways to go about interpolating with a polynomial where if you have n points, you get one polynomial, and then if someone gives you another data point, n plus 1 data point, one more, you can recycle all of your previous work. That's not how the Lagrange method works. With Lagrange's method, you have to start over and just recalculate. So it has some disadvantages, but in this class, we're not trying to learn all numerical methods. We're just trying to go through some and use them to demonstrate programming concepts. So that's what we're going to do. Okay. So Lagrange's idea is to find a set or basis of polynomials which are finely tuned so that at each of the data points of that whole set of Lagrange polynomials, or basis polynomials, one of those polynomials will evaluate to 1 at a specific data point, which I label with the subscript I. So you have a subscript I here. So there's one basis polynomial which evaluates to 1 at this point and 0 on all of the other data points. And you do that for each I. So if you have 3 data points, you're going to construct 3 basis polynomials. We'll label them 1, 2, and 3. And polynomial 1 will equal 1 when evaluated on data point 1 and 0 on all the other data points. And polynomial 2 will evaluate to 1 on data point 2 and 0 on all the others. And the same for polynomial 3. Okay, so once you have, that's the idea of these basis polynomials. The general formula is the same one that I suggested you take a picture of on the board, but I've tried to write it here. Maybe I can zoom in. Oh, that isn't going to work. Let's see here. I'll move this out of the way for a second here. Let's see, maybe if I click here and can I zoom in? No, that isn't going to work. Cool. Well, sorry, I'm trying to and equal. Okay. See if that works. Well, it didn't work. Cell size. I apologize. I was hoping I could make it larger. So the subscripts are very small here. You may have to squint your eyes. So you see in the numerator, you have x, the variable x, minus data point x1, divided by xi, when we're working on the ith polynomial, xi minus x1. And you go through that, and you have x minus x2 divided by xi minus x2, and then I have x minus x1 divided by, x minus x3 divided by xi minus x3. And you keep going. You have basically for every data point, you build one of these ratios. However, you're supposed to omit the factor where you have this xi minus xi in the denominator, because that would give you infinity. So clearly that's not going to work. All right, so you multiply them all out. And if you keep track of that, you have n minus 1 factors. So when you have n data points, you're only going to get a polynomial of degree n minus 1, as expected. All right, and you can check if you were to plug in x equals xi into this formula, it would give you 1. But if you plug in any of the other data points, say xj, where j is not equal to I, one of these factors will give 0, and so the whole polynomial vanishes. That's the basic idea for finding the basis of polynomials. And then, after you determine all of those polynomials, the final result is what you get when you combine. So the final result I'm calling y of x. And what you do is you combine the data points for y with the polynomials that are functions of x. And remember, when you plug in one of the data points, the polynomial L sub I will equal 1 on the corresponding data point. And after you multiply by the corresponding value of y, you end up with a polynomial that has the right size at each data point. So that's the idea. That's the attitude or the algorithm. Okay. So for your next assignment, which is going to be due on Wednesday, I'm losing track of the days here with all of our calendar changes. It's going to be due on Wednesday, the 25th. On Wednesday, the 25th, your assignment is going to be to write a program which will implement the Lagrange polynomial method for interpolating polynomials. And then I will want you to answer these homework questions with your function. So this will be due next Wednesday on the 25th. So I went ahead to give you some assistance here and tried to help you put together an algorithm. So the algorithm is kind of described in here. I can read it to you, I suppose. So the idea is you're going to define a function called L, which constructs the ith basis polynomial from the data. So that's going to construct, so you're going to have, because I is going to be a variable, then this function will recreate all of the Lagrange basis polynomials by changing the value of I. And then you'll create another function called Lagrange, which will pull together the data and the Lagrange basis polynomials, to pull it all together to give you the interpolating polynomial. Okay, so that's the idea. So the algorithm is broken up into two steps. One is an algorithm for the basis functions, and the other is an algorithm for how we pull things together. In class, many of you got the basis function part working, but just in case you didn't, I thought I would give you the algorithm. The idea is that so here are the inputs. The inputs to your basis functions should be an index labeled I, which represents the ith data point. Also the name of the polynomial's variable. So in the example I did above, I called the variable for the polynomial, for the domain that labels the domain of it, I called it X, but you could use whatever you want. You can make the word cat be a basis or a variable if you want. I don't know why you do that, but you know, small town, not much to do. I guess you could do that. So the user, when they call, or when this function is called, so it'll say L of I comma X. So that'll be inputted by the user of this function, or more precisely, the Lagrange function that's going to come later. And also, because the basis functions require the data to do what they're supposed to do, you have to pass them the data as input information. The next thing is to realize we want to have a local variable which will determine the size of the data. So you might remember in class, we use the dimensions command. So I'll go ahead and add that here. We'll use the dimensions command. So if you remember how that worked, the dimensions command tells you the size of an array. So if you use the dimensions command on your data set, it will tell you the size of your array. You may have to extract a little bit of information because dimensions will give you a list of numbers if your array is more than just one. You know, if it's a list of lists, then it'll give you all of the sizes. So you may have to extract out the bit of that which represents the number of data points. anyways, it's the same as what we did in class. So this idea is exactly what we did in class. Also, looking at the algorithm for the Lagrange polynomial, or sorry, looking at the mathematical equation for the Lagrange multiplier, I see that it's written as a product of many different factors. So no surprise, we're going to build it up by multiplying things. And so let's define a local variable called prod, for short for product. And what it will allow you to do is to store your intermediate steps, and then finally, it's the thing you will print out to give a return value for your function. Finally, as always, it's good to create local versions of all of the inputted quantities. That way, inside your little module, or inside your Lagrange polynomial basis function, you're not editing potentially the data, which could represent, real experimental data, and you wouldn't want to alter the files associated with that. All right. Okay. So you're going to use the dimensions command to store the number of data points in the local variable n, and then you want to initialize the product variable to be 1. When we have when we add things, we usually initialize those to start out with 0, but because we're multiplying things, we want to initialize it to be 1. Afterwards, you want to use a do loop, and you want to cycle through, and each iteration of the do loop, you're going to update the product variable, and the do loop should have n iterations. I called, in my solution, I called the iteration parameter j, but you could use anything you want, really, except for little n, because that's going to be reserved for the number of iterations. And at each iteration, you should multiply the previous value of product by this factor, x minus xj divided by xi minus xj. Remember, I is the data point that our basis polynomial is built around. And then after you do that, you should store it. You should store the result of this multiplication into product. So what happens is, after each iteration, you alter product to encode the new factor which you multiply by. And so after going through all in data points, then you will have developed a large number of factors, as is appropriate for the basis polynomial. There's one little caveat, though. Remember, going up here to the mathematical formula, we're supposed to omit the factor with a subscript I. So what you want to do is, inside the while loop, put an if statement such that says you only do the multiplication if the loop iterator j equals I. Otherwise, you just do nothing. And that will build up a product of all those factors, except when I equals j, or sorry, when j equals I, and that's exactly what you want. Finally, after you finish your do loop, you want to evaluate the final value of product one last time, and that's what you will return from your module called L. Okay. All right. After you have your module called L, you want to pull it all together to get your Lagrange polynomial. And this is a much easier thing, because it's not too surprising. The basis polynomial looks pretty gross, but the formula for the final sum is pretty nice, or pretty simple. And this is very similar to we've used algorithms like this before just to add up quantities. It's really the same thing we've seen multiple times this semester. So this Lagrange function is simpler. The inputs of it should be the variable, which I usually called X, but you could call whatever you want, and the data, which is to be fitted, because you have to pass the information to Y so that you can pull out these coefficients, and also you're going to need to pass the information to L when you use it inside Y, or inside the Lagrange function. Okay. I also define local variables to store the size of the data, again, for the same reason as before. Oh, I'm in the wrong spot, but I did that too here. So I defined in here. You might be thinking, why do I have to define in again? That's because when I did the same thing up here, I made it a local variable, which meant it was localized inside the basis function command. So I have to do it a second time in the Lagrange function. I could have just made it a global variable, but I don't know, I didn't. So this is how I did my program. And then you also need a local variable to store your final result. I called mine sum. You could call it whatever you want, but it's usually good to make the names of your variables kind of represent what they are doing in the program. So, okay, so I set in to be the number of data points. I initialize sum to be 0 before I start my loop. So before I start adding things, I want it to start out at 0, as opposed to product, which I wanted to start out with a 1. And then I used a do loop with an iterator. I called it I, which looped over all the data points. And during each iteration, I took sum and I increased it by an amount equal to the data point, the ith data point times the ith Lagrange polynomial, or the base Lagrange, the ith basis polynomial. So you just keep looping around, doing the same thing over and over and over and over and over. And when you are finally finished, it should return the final. You should print out or evaluate sum one last time after the loop to return that to the screen. And that will give you a polynomial which hits all the data points. So for Wednesday, you are supposed to construct a polynomial using this algorithm, and then use that polynomial to answer these questions. To be honest, when I was fiddling around with this, working out my own, after I had my polynomial, answering these questions probably took, I don't know, 10 minutes tops. But there you go. So that is how to construct an interpolating polynomial. And I'll talk to you guys next time. If you guys have any trouble, send me an email. You can always get me during our office hours, which are dedicated for this class, which will be Monday and Wednesday from 1 until 2. And then I'm going to be posting general office hours that any of my students could use for any subject pretty soon. I'm just trying to wait till all of this virus stuff settles down and I can be sure of my schedule. So good luck and stay healthy.